Hi, my name is Knudby. I'm an associate professor at the University of Ottawa, where I run the Shallow Water Earth Observation Lab. I also run a small company called Liquid Geomatics. In this presentation, I will show you some recent work on satellite-derived bathymetry. Satellite-derived bathymetry means estimating the depth of an area from space. There are several ways to do this. The most common method relies on bathymetric survey data to establish a statistical relationship between water depth and the spectral reflectance of pixels in a satellite image, as illustrated here. This relationship is then applied to all pixels in the image to produce a complete bathymetric map. This method tends to work well in situations where there are high-quality bathymetric data available for calibration. But when there is not, as is the case for many parts of the world, this is not a feasible approach to satellite-derived bathymetry. The work I present here is based on the idea that we sometimes need to produce a best estimate of bathymetry in the absence of survey data. And if it can be done relatively quickly and cheaply, that probably doesn't hurt either. I'm sure you can think of scenarios in which we might want to map bathymetry but don't have local survey data, like in most of the Arctic or in foreign waters, or following a storm that has rendered previous survey data out of date. To estimate bathymetry from satellite data, in the absence of bathymetric surveys, we can employ what's often called the physics-based method of Stp, which is based on the inversion of a radiative transfer model. In this approach, a range of possible aquatic environments are defined by their water depth, water quality, and seafloor spectral reflectance, as shown in this table. Given the relative position of the sun at the sensor, the spectral reflectances of this range of environments are then estimated with a radiative transfer model, and the environment whose spectral reflectance most resembles that measured for a given pixel is considered to be the actual environment of that pixel, including the water depth. We have implemented this approach into a workflow that, in principle, requires the user only to determine where they want bathymetry to be mapped, and to select a few initial settings, such as which satellite centers to base the bathymetry estimation on, what period to use data from, and a few other things. I call this FAB for fully automated bathymetry. In practice, additional operator input may be desirable, for example, to eliminate unsuitable imagery. Broadly, the workflow proceeds in 4 main steps. Once the user has defined the run parameters, FAB downloads Sentinel-2 and Landsat-8 imagery from ESA and the USGS, and pre-processes it to mask out land and clouds, automatically detects areas of optically deep water, and removes scenes that were downloaded but failed to pass some internal quality control tests. Once this is done, each scene is atmospherically corrected, and per pixel bathymetry, including its uncertainty, is estimated. Tidal information is then retrieved for each image from a global tidal model and used to reference the bathymetry to mean sea level. In the last step, the bathymetry estimates from each individual scene are combined into an ensemble product from which optically shallow water is then outlined, and comparison to validation data can be done if such data exist. FAB estimates bathymetry for individual MGRS tiles, which are 100 by 100 kilometer tiles covering all of Earth. Sentinel-2 data are directly downloadable for these tiles, making them a convenient spatial unit to work with. Landsat scenes are clipped to also cover individual MGRS tiles. So here's an example from Lizard Island in Australia. FAB downloads all the imagery from the relevant MGRS tile, including lots of imagery that is partially but not fully cloud covered. The idea is that each image has information that can contribute to estimate bathymetry for some pixels, and except in extreme cases, all pixels are cloud-free in some images. So if we combine the information on all images in an intelligent way, we should be able to get a good estimate of bathymetry for the entire area. To do so, we need to mask out all the land and clouds in each image, which is done based on the reflectance in the shortwave infrared wavelength. This process also masks out boats and other floating objects, and in more northerly areas it can also mask out sea ice. Some very thin clouds are not currently masked, and neither are cloud shadows. Once the imagery has been pre-processed, atmosphere correction is used to remove the effect of the atmosphere and estimate the reflectance of the water body itself. And this reflectance is what is inverted in the bathymetric model to estimate the water depth. This is done on a per pixel basis for each image. And then in the end, the results from each individual image are combined to produce a single ensemble depth estimate for each pixel, along with a per pixel 90% confidence interval. In the initial development of this workflow, we tested it on 5 sites, ranging from the Arctic to the tropics. Between then and now, we've run it in a few more places, like further north in Canada and in murkier waters in the St. Lawrence River, and we're currently doing a test at 7 Arctic sites. Results are generally rather promising when we compare our estimates to validation data from bathymetric surveys. As is shown here from 2 sites, Cambridge Bay in the Canadian Arctic and Icesat Island in Australia, the ability to precisely estimate bathymetry is okay up to a point where RMSE values are around 1 meter, and then it breaks down as we move into deep water, where the spectral reflectance of the pixels is no longer a function of water depth. To avoid making erroneous bathymetry estimates for depth where FAB doesn't work well, we investigate the width of the 90% confidence intervals, and we set a threshold that eliminates all data beyond the depth that corresponds to a given interval. An example is shown here. Confidence interval ranges are shown with red arrows, and a threshold that eliminates all data from depths where the confidence interval range is greater than 3 meters is shown with a horizontal red line. Other approaches exist to masking out optically deep water, and we're always looking to further refine this work. Here's an example of where FAB really could have been useful a few years ago. In the summer of 2018, a vessel with 163 people on board ran aground on the rock you see in the middle of this image, which is located in the Canadian Arctic. It spilled some fuel oil, the rescue cost more than $500,000, and I'm told the company who owned the vessel is now bankrupt. I've highlighted the rock in the red circle here, but it's important to note that the nautical chart at the time didn't show the existence of shallow water here, and the 2 nearest survey points showed 70 and 90 meters water depth respectively. Nonetheless, the rock was clearly visible on satellite imagery since 2016. When we run this MGRS tile through FAB, the rock is clearly estimated as being relatively shallow, somewhere around 5 meters at its shallowest point. In fact, many other shallow underwater features are also quickly identified. Now, after the ship ran aground on the rock, the immediate area has been surveyed and the nautical chart of the area has been updated to show a depth of 5.2 meters. But wouldn't it have been nice if something like FAB could have at least been used to flag the area as a concern, maybe as a priority to survey, and vessels could be made aware that the nautical chart perhaps should not be trusted in this area. Here's another example from an area in the western part of Hudson's Bay. This is one of those areas that have a large number of shoals, and we can see that FAB works well to find them. And when we apply the threshold method I mentioned before, we can create a simplified product that simply outlines shallow areas and separates them from deep areas. With workflows like this one, there's always additional work to do, refinements to be made, and additional tests to be done. Our plans for the immediate future focus on a couple of things. The atmospheric corrections implemented in FAB up to now operate on a pixel-by-pixel basis and are unable to account for the influence of nearby land on the spectral reflectance of a water pixel as observed from space through a scattering atmosphere. This has a non-negligible influence on our ability to estimate bathymetry in several environments, like fjords, deep bays, and especially in inland waters, anywhere the water in question is surrounded by lots of land. But the physics behind this phenomenon are well understood and a correction is under development. NASA's Icesat-2 Satellite is a space-based LiDAR that can, under many conditions, produce direct point measurements of water depth. Integration of these data into the FAB workflow is a priority and will likely serve to improve the existing accuracies. Turbid water is currently a challenge for the workflow, and additional components to the data processing will likely be needed to flag and eliminate turbid water. And finally, FAB was developed to be quick and cheap to apply over large areas, so that's what we aim to do over the coming years.